Hi everyone, my name is Sifat Muhammad Abdullah. I am a fourth year PhD student in computer science at Virginia Tech. So today I'll be presenting our paper, which is in collaboration with researchers from Virginia Tech and UT San Antonio. So there has been a ton of work in the deepfake image detection space, but today we want to discuss some evolving security threats that are plaguing the field of deepfake image detection. So let's get into our work. First of all, what are deepfake images? They are fully synthetic images created using deep generative models like GAN, StyleGAN, and Stable Diffusion. Right now, generating a deepfake image is as simple as typing in a text prompt thanks to tools like Stable Diffusion, Midjourney, and DALL-E. For example, we see two sample images from Stable Diffusion and DALL-E here of a fox dressed as a saint and a shark attack in a desert. Now, these are deepfake images, but it just shows how easily anyone can create an image with any content using just text prompts. So, deepfake images have a lot of benign applications. For example, teachers can create more engaging educational content for their students. Deepfake images also promote creativity as anyone now online can create high quality artwork. Advertisers can also use deepfake images to create more engaging commercials, and it's used in many more applications. While deepfake images have benign applications, they can also be misused and pose serious security threats. For example, deepfake images can power fake accounts in social media. Adversaries can also create convincing fake news articles with deepfake images. For example, anyone can create an image of someone doing something that they never did, which can be highly problematic. There are other security and privacy violations as well. For example, an adversary can spoof the identity of someone else for their own financial gain. In fact, deepfake images pose threats in both public and private sectors, because of which we see US federal agencies are advising on deepfake threats, and even the White House is pushing private tech companies to build more robust and reliable deepfake defenses for better AI governance. So now the question is, are defenses now robust in detecting such deepfake images? Well, to answer this question, we study 8 state-of-the-art defenses, which are all supervised classifiers with very diverse methodology and very high detection performance, as seen on the third column here. Particularly, I want to draw your attention to an exciting development in this space, which is the UNIFClip defense published last year in CVPR. Now, UNIFClip is a new class of defense which leverages Vision Foundation model features. So you may ask, what are Vision Foundation models? They are models trained on internet-scale large datasets using self-supervision and then further adapted or fine-tuned for downstream tasks like image classification, object detection, object localization, etc. Some examples of foundation models are CLIP, VIT, and EfficientNet published over the last few years. Now let's look at UNIFClip, which leverages features extracted from the CLIP foundation model. Note that a foundation model is not specifically trained for deepfake detection, but UNIFClip shows that features from such domain-agnostic foundation models are applicable for deepfake detection. So now that we have some idea about the deepfake image detection space, let's look at our work where we analyze 3 key requirements to build an effective defense. So the first question we ask is, are defenses following the best practices for effective training and evaluation? Here we identify issues with many of the defenses that we will discuss in future slides. Second, can defenses generalize to deepfakes from different generative models? Here, the emergence of user-customized models pose serious threats to the generalization performance of defenses that we will discuss. And finally, are defenses robust against adversarial attacks? We see foundation models can be easily used to create effective adversarial fake images that we will discuss. So now let's analyze each of these 3 key requirements and discuss their issues. So for the first one about defenses following the best practices for effective training and evaluation, let's focus on the UNIFClip defense, where we see a lack of control for content and quality of images in the training set. For example, if all real images are of eggs and all fake images are of humans, then a classifier may not learn the necessary features for deepfake detection. Moreover, the fake image in Uniflip dataset is of very low quality, which is why the real and fake image features are easily separable, which results in a very high accuracy of 94%. But if we evaluate the same Uniflip defense on a new dataset where we control for content and quality, the real and fake image features are not as easily separable, which results in a much lower accuracy of only 49%. So this is a serious issue, and we solve it by fine-tuning all of the 8 defenses in our study on our high-quality datasets for their proper evaluation for the rest of our paper. Now let's look at the second critique which is lack of adversarial evaluation. Now, if a defense has to be deployed in the real world, well, an attacker will try to break the defense. The attacker can craft adversarial samples in a black box setting because the attacker may not have access to the defense model. But existing work is severely lacking in this respect, which is why defenses going forward should be evaluated against adversarial attacks where an attacker is actively trying to break the defense. And our final critique is the use of restricted image content types. Defenses now are only trained and evaluated on only human face images. But now deepfake images can be of anything that we can imagine. That's why defenses going forward should be evaluated with diverse image contents. Now let's look at the second key requirement of generalization and how user-customized models pose threats in this respect. Previously, defenses were only evaluated with a few generative models like a GAN and a diffusion model. But now there has been an emergence of user-customized models, which means users are customizing generative models according to their own preference and liking, which expands the threat surface significantly. That is why we study generalization of defenses against such user-customized models, where we take Stable Diffusion as a case study. We see there are already over 3,000 user-customized Stable Diffusion models on CivicAI and Hugging Face platforms, where users have used lightweight LoRa fine-tuning strategies to customize the models. Now, you may ask, why do users customize models in the first place? Well, because each user can have unique preference. For example, for a sample fake image from the base Stable Diffusion model, users have created LoRa models to alter certain properties like varying the sharpness of the image, adding more detail to the image, reducing noise, or varying the brightness of the image. Note that the LoRa models only alter certain properties without varying the high-level content of the image. So now, if a defense is trained and optimized for the base Stable Diffusion model, how well do defenses generalize to such user-customized models? So for evaluation, let's first look at Uniflip, which claims to be state-of-the-art in generalization performance. So we collect several models and here show results for 8 user-customized Stable Diffusion models from CivicAI. So in the graph here, along the x-axis, we plot the 8 user-customized Stable Diffusion models, and along the y-axis, we plot delta R, which is percentage degradation in recall of fake images. Note that high degradation is bad for the defense. So despite claiming good generalization, Uniflip shows significant degradation in recall with an average degradation of 42.6% and a maximum degradation of 64.5%, which is highly concerning for a defense which claims to be state-of-the-art in generalization performance. In fact, except one defense, all of the other defenses in our study show poor generalization with a maximum degradation of 64.5 to 90%, which just highlights the seriousness of the problem. Only the DCT defense, which leverages artifacts in the frequency spectrum, show the most promise with an average degradation of 19.6% and a maximum degradation of 23.5%. So DCT is comparatively better than other defenses, but there is still scope for improvement. Recall that defenses using foundation model features like Uniflip claim to have the best generalization performance. That's why we fuse features from domain-agnostic foundation models with domain-specific frequency features by ensembling Uniflip and the DCT defense. And we see an improvement of average degradation from 42% to only 8% after ensembling, which means It is more effective when features from domain-agnostic foundation models are combined with domain-specific frequency features. We also try other ways of improving the generalization performance. Now, most defenses actually extract features from the content space or the image space. For example, the DCT defense. This extracts the image frequency features given an image and then trains a linear layer for deepfake detection. But can we use content agnostic features? Or can content agnostic features help improve the generalization performance of defenses? Well, there is prior work that shows that noise space, which is the residual image after removing all the content, can contain effective discriminatory features or patterns for deepfake detection. That means there is some potential here. That is why we augment the DCT defense with content agnostic noise features. So how do we do it? By additionally leveraging the frequency spectrum artifacts of the corresponding noise of the image as well. So given an image, first we extract the corresponding noise of the image and then extract the noise frequency features, followed by a feature augmentation with the image frequency features. And finally, we train a linear layer for deepfake detection. Now let's look at the results. Across 16 of our user customized stable diffusion models, the average degradation improves from 19.7 to 16.7%, which means there is potential for improvement here. That is why we suggest combination of better noise extraction schemes and better learning strategies can improve the generalization performance further. Now let's look at the last question of, are defenses robust against adversarial attacks? A traditional idea in this case is to add adversarial noise to create adversarial fake image, but that can significantly degrade the image quality as we can see here. So, can we create adversarial images without adding any noise? So for a given face image, we tried arbitrary prompt modifications with the style clip model to perform careful semantic changes like adding lipstick to the face, while preserving the high-level content. For example, in this case, even after adding lipstick to the face, it's still a human face. Surprisingly, when we evaluate the image on the right against the DCT defense, it's wrongly detected as real. That means it is possible to create adversarial fake images with such careful semantic changes while preserving the high-level content and adding no noise. The question is, can we systematically create such adversarial fake images? The short answer is yes. Leveraging foundation models, we can create such adversarial images. So let's look at an example. For a given fake image and a style clip generator, we adversarially update the generator driven by a prompt to generate the adversarial fake image. Note that the adversarial update of the generator combined with the semantic change, in this case the smile, helps create the adversarial fake image. So that's how we can generate adversarial images by such careful semantic changes without any added noise. So how do we adversarially update the generator? With the help of a surrogate deepfake classifier which extracts features from a foundation model. Note that our adversarial attack is a fully black box attack with absolutely no queries to the victim model. So let's look at some image samples here. This pair of sample is for a face with a smile. This is for a face with lipstick. And this is for a face with glasses. Note that there is no added noise, but there is only some careful semantic change. Our attack is very low cost, where an attacker can generate over 800 adversarial images with only $10 using the NVIDIA A100 Cloud GPU resources. So before going into the results, let's discuss about our surrogate deepfake classifiers. So our adversarial attack is powered by surrogate deepfake classifiers, which are built using foundation models. So the first foundation model we used is EfficientNet, which is trained on 14 million images. And the second model is ClipResNet, which is trained on 400 million images. So now let's look at the results. How effective are these adversarial images? So we will show results against the two surrogate deepfake classifiers from the previous slide, EfficientNet and ClipResNet. So along the x-axis, we plot the 8 defenses that we study in our paper, and along the y-axis, we plot delta R, which is percentage degradation in recall of fake images. Note that high degradation is bad for the defense. So against EfficientNet, we see pretty significant degradation for almost all the defenses. But against ClipResNet, which is a foundation model trained on a larger dataset than EfficientNet, we see more degradation of all the defenses across the board. That means a foundation model trained on a larger dataset is more effective for attack. But note that UnifClip shows less degradation compared to the other defenses. And recall that UnifClip is a defense that uses features from foundation models for deepfake detection. So now let's focus on a scenario where both the attacker and the defender uses foundation models. For example, in our adversarial attack, we used ClipResNet, which is trained on 400 million images, and EfficientNet, which is trained on 14 million images. Whereas the UnifClip defense uses a foundation model called ClipVIT, which is trained on 400 million images. So now, what if the defender uses a more powerful foundation model? So we upgrade our UnifClip defense and call it the UnifConf2B defense and change ClipVIT to a new foundation model called the OpenClip ConfNext large model, which is trained on 2 billion images. So now let's look at how effective will be a defense which uses a more powerful foundation model, which in this case is the UnifConf2B defense. So against both of our surrogate deepfake classifiers, ClipResNet and EfficientNet, the degradation of UnifConf2B defense is only 0.1%, which is very impressive performance. That means a defender using a foundation model trained on a larger dataset is more effective. We also try other ways of improving adversarial resilience, one of which is adversarial training. So we adversarially train the 3 most robust defenses and then perform adversarial attack with our strongest surrogate, the ClipResNet model. So here we'll show the results in this graph where along the x-axis we have the 3 most robust defenses. So before adversarial training, we have some pretty significant degradation. But after adversarial training, the degradation drops for all of the 3 defenses. That means adversarial training can help improve adversarial resilience against our attack. So it seems like adversarial training is a permanent solution, but it should be noted that the attacker can adapt their strategy to substantially alter the distribution of adversarial samples, which can disrupt the defenses. So now that we have almost covered all of our paper, I'll conclude my talk with some challenges and opportunities. Evolving customization techniques of generative models is a real threat for generalization performance of defenses, and advances in foundation model can be weaponized to fool deepfake defenses, as we have shown in our paper. Moreover, the lack of deepfake datasets covering a wide variety of content types is detrimental for effective defense training, which is why defenses should be trained and evaluated with diverse image contents. But there is still hope. For example, we suggest ensembling foundation model features with domain-specific frequency features can help improve generalization performance, and leveraging powerful foundation models can help enhance robustness against adversarial attacks. Moreover, defenses going forward can use our simple and low-cost attack strategy using foundation models to benchmark their adversarial robustness. Our code, model, and datasets are available in this link. Feel free to contact me through my email if you have any questions. Thank you so much.